Welcome to The Explainer. So glad you're joining me. Today we're tackling a deeply relatable and honestly viscerally frustrating problem. If you've recently put together a rig to run local language models, you know the exact moment I'm talking about. You load up a real model, hit enter, let it do its thing, and suddenly, your local LLM rig sounds like a Boeing 747 getting ready for takeoff. The room heats up, the fans are just screaming, and boom, your peaceful environment is totally shattered.
It's a frustrating reality, right? The quote here really hits the nail on the head. A high-power AI workstation can turn a quiet home office into something that sounds like a server closet and feels like one too. Absolutely true. But hey, don't worry. You literally don't have to live with a screaming server in your living space. In this explainer, we're going to walk through a highly actionable roadmap so you can reclaim your quiet home office, tame that heat, and finally silence the noise.
Okay, let's dive right into this. Section 1, the paradigm shift, gaming versus AI workloads. To fix this whole heat issue, we really have to understand the fundamental misunderstanding most PC builders have about thermal management when it comes to AI. It actually requires a complete paradigm shift.
We're dealing with two completely different types of workloads here. On the gaming side, it's a bursty load. You get into a big firefight, the GPU spikes to 100%, but then you hit a loading screen or pause the menu and it idles back down. It's essentially a series of sprints. Your cooling system gets regular breaks to catch its breath. But AI inference, that is a marathon. When you run a batch job or set up an agent, the GPU runs flat out, continuously, sometimes literally for hours. There are no loading screens. The cooling system never gets a chance to catch up because it's handling sustained output, not just an average.
And when we say sustained output, we're talking about massive amounts of power, 800 watts plus. Think about that. A dual GPU rig can pull over 800 watts continuously, and that's before you even factor in the CPU. Why does that matter? Because every single watt of power your machine pulls from the wall literally becomes a watt of pure heat just dumped straight into your room.
So where exactly is all that heat coming from? Well, you can't reduce what you can't locate. Looking at the breakdown, the GPU is absolutely the main event here. It's responsible for roughly 70% of your total thermal load during local inference. Your CPU, which handles the prompt processing, makes up about 20%, and then your power supply and voltage regulators quietly had that last 10%. The takeaway? If you want to drop those temps, you absolutely must focus on the GPU first. It's the biggest piece of the puzzle.
Which brings us to Section 2, the reduction framework, levers in order of impact. We aren't just going to buy random fans and hope for the best here. We're going to follow a waterfall of solutions, tackling this problem systematically from the highest impact changes all the way down to the lowest.
So here is your mental map for the rest of this explainer. Step 1, we're going to undervolt and cap power. Step 2, match the cooler to the workload. Step 3, fix the airflow. Step 4, tune your software and hardware for quiet operation. And finally, Step 5, relocate the machine if all else fails. Let's walk through this step-by-step framework so we can actually silence your machine.
Step 1 is what I love to call the massive free lunch, undervolting. You see, modern GPUs ship tuned to hit maximum benchmark numbers right out of the box, which is honestly incredibly inefficient. By lowering the voltage and capping your power limit down to, say, 70 or 80% of its maximum, you drop tens of watts of heat instantly. And the absolute best part? Because local inference is largely bound by memory bandwidth, not the raw core speed, you lose almost zero performance in tokens per second. Actually, scratch that. It's practically unnoticeable. It is literally free cooling.
Let's move on to Step 2 and see how this all builds together. Once you stop producing all that unnecessary heat, you need to match your cooler to that sustained marathon workload we talked about earlier. Gear that's good enough for gaming completely fails here. For your CPU, you're going to need a serious dual-tower air cooler or a massive liquid AIO. And as for the GPU, well, those oversized triple-fan gaming cards really struggle when stacked together in a case. This is exactly where workstation cards, like those blower-style GPUs that are specifically engineered to run flat out while packed densely, actually win the thermal battle.
Now for Step 3, airflow. And this is a really counterintuitive reality that trips up a lot of builders. You might naturally think, oh, I'll get a sealed, sound-dampened, silent case. But for AI workloads, a sealed case just traps that massive, continuous heat, which slowly cooks your components and forces your fans to just scream at max speed to keep up. On the flip side, an open, airy mesh front case lets that heat flow right out. Because the fans don't have to fight for every single breath of air, a mesh case is surprisingly quieter. Total game changer.
Step 4 is all about tuning. And interestingly enough, it's not about buying new hardware. Setting flat, smart fan curves in your software turns out to be the biggest free win for your ears. Instead of your fans surging loudly every single time the temperature blips, a flat curve holds a steady, quiet speed. You can also apply high-quality thermal pads to your GPU, decouple the case from your desk to stop those annoying vibrations, and honestly, just move the tower to the floor. Simple as that.
And while we're optimizing our hardware, do not forget this massive number right here, 1200 watts plus. So the Christian point is, pushing a 750 watt power supply near its absolute limit continuously is this hidden, terrible source of both heat and noise. It's going to spin its fans super aggressively and just shorten its own lifespan. If you're running high-end AI hardware, do yourself a favor and plan on a generously sized power supply of 1200 watts or more, just so it barely breaks a sweat.
We've covered the framework. Now it's time for Section 3, picking your priority, silence versus performance. You don't have to do everything we just talked about. You really just need to pick your path based on your personal tolerance for noise versus your need for speed. If you want a rig that shares your office and pretty much vanishes into the background entirely, you're going to want the quiet above all setup. The recipe here is pretty simple. Undervolt and power cap your GPU hard. Set flat, conservative fan curves, install a top-tier air cooler inside a mesh case with large, slow-spinning 140mm fans. Now, you'll have to accept a small hit to your absolute peak performance, but man, the trade-off is beautiful, near silence.
Now, the alternative path is chasing maximum performance. If you run dual GPUs on air, heat buildup can cause a really painful 10 to 15% thermal throttling penalty on your inner cards. To prevent that and keep every single token per second flowing, you'll run it at full power, use liquid cooling for the CPU, grab Workstation-class GPUs, and set super aggressive fan curves. It is going to be loud, for sure. You might even need to leave the room. But hey, you get exactly what you paid for in pure throughput.
For most people, however, the answer lies right in the middle, the balanced setup. You do a modest GPU undervolt for an easy efficiency win with almost negligible performance loss. You pair a great air cooler with a mesh case, dial in some sensible fan curves, and maybe throw in some cheap acoustic dampening. This keeps the rig right there in your office, noticeably cooler and quieter without sacrificing your model speeds. It's really the sweet spot.
But what if you've done all of this and it's just still too much? Well, that is our final lever, the platform trade-off. You might just need a fundamentally cooler architecture altogether. An Apple Silicon Mac Workstation features unified memory and runs on a fraction of the power, making it practically silent sitting right on your desk. On the other hand, a traditional GPU tower gives you massive raw throughput, but as we know, generates high heat. Sometimes switching platforms entirely is the ultimate noise reduction strategy. Before you start tweaking anything, though, remember this golden rule. Measure, don't guess. Human instinct simply isn't enough here. An unmeasured change that sounds a bit quieter to your ear might actually just be your GPU silently thermal throttling in the background, meaning you just took a massive step backward in performance. Use software to check your actual temperatures and clock speeds, and pull up a sound meter app right on your phone to track real decibel changes. Trust the data. So AI inference doesn't have to mean living next to a jet engine. By capping power, fixing that airflow, and matching your cooling to the marathon nature of the workload, you literally have total control over your hardware's acoustics. So my final question to you is this. Will you apply this framework to tame your workstation today? Or are you just going to surrender and move it to the closet? The power is totally in your hands. Thanks so much for joining me on this explainer, and happy building.